some discontinuity with the electrics or electronics of these devices. Okay, so this was a final report of the Helmut study, which was the reason to rethink about the amount of drug dosing. And especially fentanyl was then used for the maintenance of anesthesia. This was a time of so-called neuroleptic anesthesia or neuroleptic analgesia and high-dose fentanyl anesthesia, especially for cardiac surgery with so-called huge industrial doses of fentanyl. This led in turn to an increasing occurrence of post-operative apnea and even death. In 1974, Cascade and Gravenstein draw attention to this complication in an editorial entitled Silent Death. More than 1 decade, the topic silent death determined the agenda of the scientific discussion about the value of IV anesthesia. 5 years after this editorial, one surprising possible cause of the silent death was reported, a particularity of the pharmacokinetics of fentanyl, namely the secondary rise of plasma concentrations after around about 90 minutes, as investigated by my friend Jürgen Schüttler and my then chief, Horst Stöckel. As a consequence of this finding, and the fear for post-operative apnea led to a remarkable reservation with respect to anesthetic drug dosing. This brought another big problem, intraoperative awareness. The problem was big because it became very expensive when in 1985 a British mother was awarded some £10,000, a huge amount at that time, as compensation for experienced severe and prolonged pain during cesarean section. At that time, Professor Michael Rosen in Cardiff was treasurer of the Faculty of Anaesthetists of the Royal College of Surgeons, today Royal College of Anaesthetists, and he feared a tremendous increase in insurance rates and therefore organized a symposium on consciousness, awareness and pain in general anesthesia. Thus, the mid-80s may be considered as a starting point for search for physiological parameters measuring the depth of anesthesia, detecting awareness, and thus allowing to survey the therapeutic goal achieved. These mishaps could be prevented if one were able to predict the drug concentrations or even the drug effect in the future. Predictability in this context means that the laws governing the time course of drug action after the delivery of drug into the central circulation of the human body are reliable and have a reasonable inter-individual variability. Given the knowledge of such laws, they may be used to construct drug delivery schemes which aim at the appropriate targets and thus may be helped to prevent over and underdosing. What are the laws relating drug dosing to drug effect? This figure depicts today's conceptual understanding of the relationship between drug dosing and the ultimate clinical effect, and the possible targets which are currently used in the clinical practice of anesthesia. It is common sense to subdivide this pathway into pharmacokinetics and pharmacodynamics. These terms are often explained by the aphorism, pharmacodynamics is what the drug does to the body, and pharmacokinetics is what the body does to the drug. The pharmacokinetics of intravenous anesthetics were first investigated by these two gentlemen, Bernard Brodie, called Steve Brodie, and among others, Emmanuel Pepper, called Manny Pepper. Our today's understanding of the pharmacokinetics of a drug is summarized at best by the well-known multi-compartment model, typically a 3-compartment model, which has led to computer-aided drug delivery systems called TCI, Target Controlled Infusion Systems. Most of today's TCI systems, which are used in clinical practice, are based on these formula, from which one may derive specifically tailored drug dosing schemes. For instance, a scheme which establishes a constant concentration, also known as BET scheme. After the initial bolus, the rate of infusion is composed of 2 parts. A steady-state infusion rate, and then an exponentially declining infusion rate, which compensates for the net transfer from the initial compartment to the other compartments. This has to be contrasted to much earlier dosing strategies, which are depicted here in a simulation. All of them use as maintenance dose the infusion rate to maintain steady state, but they differ in the size of the loading dose. Verosovsky used the loading dose just to fill up the initial central compartment, but then you have here a dip, and this dip can cause, for instance, has a risk of awareness. And therefore others said, okay, we need not to fill up the central compartment, but we need to fill up the entire body. We have to give the entire body load. But giving the entire body load results in very huge concentrations. And later said, okay, we have to give the body load at a short infusion. But even then, you have here very high concentration and maybe an overdose. And the BET scheme was just a scheme which takes the balance between the Berezovsky approach and the Wigner approach. In practice, however, one has to adapt the concentration according to the surgical state and the condition of the patient. And this slide here is our assembly of pictures, and it takes some time for these figures to be loaded. This shows the development of intravenous drug delivery systems from the 17th century, the first hollow needle, to the computerized development nowadays. Instead of controlling drug concentrations, one could choose to use drug effect. If the drug effect can be immediately measured, one might consider to use closed-loop feedback-controlled drug administration. The idea of closed-loop feedback control begins to gain ground in anesthesia, and here are an assembly of papers of the last years. And I think there is some enthusiasm to proceed in this direction. It has been proven that feedback-controlled anesthetic dosing might be a useful research tool. For instance, to study inter-individual variability in drug requirements, whereby each patient is treated at the exact same level of drug action. And here is such an approach where you have here the constant effect established in a number of patients, and then we get here the resulting requirements in each individual patient, and you can immediately here see the inter-individual variability, whereby each patient or person was treated at exactly the same level. The proof, however, that the feedback system can be made to a useful approach in patients' care remains, however, to be seen. At least if one considers the fact that as early as 1950, Pitfalls and others describe EEG-based closed-loop systems. One has to pose the question and has to carefully analyze it. Why is, after nearly 60 years, no pharmacodynamic-based automated feedback control system for anesthetic drug delivery available? As the necessary investments are deemed too high, and the anticipated return of investments too low, or may it be better for a patient and even our specialty if we proceed from target concentration to target effects and let the loop not close automatically, but by an anesthetist? One should reflect about that question. But maybe another reason is we have not identified the right targets. EEG-driven entities, like for instance median EEG frequency or so-called BIS values, do they really reflect the depth of anesthesia, the ultimate target, which we would like to control? What we have learned during the past decade is that anesthesia is a multidimensional entity which induced with several drugs, in general at least two. This scenario is much more complicated than the one drug, one effect scenario of the first simple feedback system. A first minimal and realistic way to work out such a complex concept has been started by Schäfer and Stansky. They consider depth of anesthesia as a resultant of the interaction of two drugs involving a hypnotic component creating unconsciousness and an analgesic component that decreases the body's reflex responses to noxious stimuli. In analogy to the concepts of quantum theory, we proposed some years ago to define depth of anesthesia as a transition probability between states due to some kind of stimulation. In this slide, the state star 0 here defines an appropriate anesthetic state with a blood pressure of 90 millimeters of mercury, a median frequency of 4.5 Hertz, and so on. And this state is altered by stimulation to a state with blood pressure of 130 millimeters of mercury, a median frequency of 7 Hertz, and so on, which may be considered as an inadequate state for surgery. So we have a transition from this perfect state star 0 to the improper state star 1. Finally, one has to sum over all such possible inadequate states, here labeled star 1, to get the final transition probability. Surely, this is a fine concept, but really hard to realize. Schäfer and Stansky use a very similar, but more simple definition, namely the probability of no response to stimulus. But even that might be hard to determine. But one may use an approximation to this probability. And here now, the EEG monitoring may be again introduced. Maybe, for instance, the value of the BIS index or median EEG frequency or approximate entropy of the EEG could be an approximation for the estimation of this probability. Hence, to characterize the pharmacological state of the patient treated with an hypnotic and an analgesic compound, we could benefit from three numbers: the biophase concentration of the hypnotic, the biophase concentration of the analgesic, and the intensity of the chosen effect. Why? What is a state space? This term originates from classical mechanics and denotes the set of all possible states of a dynamical system. Gibbs introduces in 1901 also the term phase space. I may exemplify my reasoning by looking at the pharmacokinetics of propofol as a dynamical system. Look first at the upper part. Here are the well-known three differential equations for the three compartments formulated with the three amounts of propofol. Given the initial conditions, say at time 0, there is always 0 in all compartments, and then you give at time 0 150 milligrams as bolus into the first compartment. So at time 0, you have 150 milligrams in the first compartment, 0 in the second compartment, and 0 in the third compartment. And then you have the initial conditions that can solve these equations. And you know all the solutions. You see here the exponentially declining amount of drug in the first compartment, and then the increasing amount of drug in compartment 2 and 3, which then decline in the future. Now, the state space of propofol is considering these three amounts of drugs as coordinates in a three-dimensional space. And if you look at this in the three-dimensional state as coordinates, then you get a trajectory. And here you see the black part here is a trajectory of the 150 milligrams of propofol. No, here. Of 150 milligrams, and you see how from the 150 in the first compartment, the trajectory fills the second and third compartment, and finally it goes down to the, let me say, the trivial attractor of this dynamical system, 0 here in all compartments when all of the drug has left. And you see here, to each point in the state space it corresponds one trajectory. If you have once reached this state here during some surgical operation in anesthesia, then if you stop a dosing, then the system will go this way, and finally and eventually it will reach 0 here. At any moment in time, the pharmacokinetic state of propofol is uniquely described by a point in the state space, and the differential equation defines a unique trajectory in this space. And the following two slides gives you some other spaces, some other trajectories in phase space. Here for a concentrated fusion, which was stopped here, at this point here, and then you see here how it turns to 0. And the next shows the trajectory for a BET dosing scheme, where you have all over the time, here this amount of drug here. The time information is missing, so that the entire time of the BET state maintaining this amount of drug in the center compartment is collapsed only to this point, and then you see how this trajectory evolves. Actually, the TCI pumps which I use today steadily calculate these trajectories, namely the three components, the three coordinates. So they show in only, in general, one concentration. The essential point is, given one point in state space, one can determine the entire future of the pharmacodynamic system by the given differential equation. Coming back to the state space monitoring of anesthesia, we have to include the effect side of our biophase concentration and thus end up with a four-dimensional space for each drug. For two drugs, the hypnotic and analgesic, this will be 8 dimensions, plus the effect dimension gives 9 dimensions. As we cannot represent an Euclidean 9-dimensional space, one may proceed like the TCI pumps and depicts only the two biophase concentrations and the effect concentration, onto which the trajectory is projected. And this is shown here. Here are the counter lines for diverse effects, and here is the projection of this trajectory state space. Such approach, which has been realized by the Johannes and Byrne group in collaboration with Strager, as I have said here. The missing effect dimension, which is missing here, may be projected as counterlines onto the concentration plane, as I have just shown, which are in essence the isomodes of the two drugs for different levels of effect. The limitation of these methods is that it naturally confined to two drugs, and it remains to be seen whether the future of general anesthesia will stick to not more than two simultaneous drugs, or whether 3 or